Welcome to SoundWaves, year 15. Thanks so much. I'm Daniel Graboy, and I created this series 15 years ago with the idea that people like music and they also like learning stuff, so why not combine those two things? And here we are, well over 50 departments represented at SoundWaves, and an incredible variety of musicians, and tonight will be a real treat as well. I want to thank our sponsors. I know they're printed on your programs, but I want to read them off anyway because they've been so generous and wonderful in their support. So what I really should say is, in addition to welcome to SoundWaves, welcome to the Wisconsin Science Festival, and welcome to Klez Fest Midwest. We also have support from the Mead-Witter School of Music, of course, which we are currently sitting inside of, the Meyrent Institute for Yiddish Culture, the Connie Project on Jewish Arts, the Mossy Weinstein Center for Jewish Studies, and Wart FM. So let's give it up. By popular demand, we have a lot of music, and our musical guests who are here from New York City are just amazing, and you're not going to believe what you hear. And then in the past, we've typically had 4 lectures, but we're only having 2, plus me, but I don't count, and so that we can have a lot of music. So I'm sure you're going to really enjoy the evening, and please join me in welcoming David Krakauer and Kathleen Tagg.
Thank you. We're going to begin with a piece called Hasidic Dance by Abraham Elstein. Abraham Elstein... Oh, the microphone. Oh. This one or... Yeah. Oh, okay, there, it's on. We're going to begin with a piece by a composer named Abraham Elstein. The piece is called Hasidic Dance, and Elstein was well known for his work in the Yiddish theater. He wrote actually a lot of hits for the Yiddish theater. He also did the music for one of the most important Yiddish films of the late 30s called Yidel mitten Fiddle, from 1937, starring Molly Picon, who, all right, Molly Picon fans out there. And Molly Picon also, you could see her on episodes of Car 54, Where Are You?, which is pretty amazing. So anyway, this piece is a little bit of a mixture of klezmer, light classical, and there's even some sort of, let's say, epic moments that sound like the score from Ben-Hur. So this is the Hasidic Dance by Abraham Elstein.
Okay, hello everyone. So I'm Danny Fredrickson, and I'm going to show you something quite different. So I'm a chemist in the chemistry department here, and when I was asked about the idea of talking about something on the atomic scale, my eyes just lit up and thought, I know something about the atomic scale. And so what I'd like to tell you a little bit about today is about the kinds of things that can happen when you mix metals together to form new kinds of compounds. And so this is what I call when the atomic scale goes big. So atoms that can do things that get really, really big. So people have been mixing metals together for quite a long time. We can look back into the Bronze Age, 3,600 BC or so. So here are just some examples. This is the first known bronze flag from Persia. Here we have a silver vessel. Here we have a nice bronze artifact here as well. And so you can see that we've been doing this for a long time, and as time has gone on, we've continued to be interested in what's going to happen when we mix different things together to get new things out of this. But over this time, we've gotten more sophisticated in terms of our methods and our ideas, and also really on our focus, not in terms of what happens if I mix this clump with this clump and see what comes out, but actually thinking about what's happening to these things on the atomic scale, right? And so what do I mean by the atomic scale? Well, let me just tell you first that these are some of the kinds of things. Now we're not really thinking about what is this going to make this material harder? What's going to make it bend better, right? But now we're thinking about much more interesting properties, such as being able to conduct electricity without any sort of resistance, or the idea of taking solar light and turning it into electricity, or to be able to turn temperature gradients into electricity. So here's an example of the Voyager spacecraft, which has now left the solar system, right? And how has it been going this long? Well, it has a thermoelectric generator in it, where it basically has a material that when it's exposed to a temperature difference, such as the temperature difference between a radioactive source in the middle of the satellite and the coldness of space on the outside, right? It can churn that temperature difference into a voltage without any moving parts, and they can keep this thing going for 40 years or more, right? And so being able to do this kind of stuff leads us to think about, well, what's underlying this are going to be the arrangements of atoms in these materials. Let's try to find new types of arrangements. And so, again, what do we mean by the atomic scale? Well, I have some pictures here. So in our lab, we like to make new materials and new metals and things like that. If we're really lucky, we might get crystals that look like this. This is a millimeter scale bar. These are crystals of something we call sodium cadmium 2. So I would call this the macro scale. This is something you can pick up and hold in your hands. You can measure it with a ruler, right? By contrast, here's what we have in terms of the atomic scale. So this is a methane molecule like you might use to heat your house for natural gas. The distance between this carbon atom here and this hydrogen atom here is what we call 1 angstrom. This is 10 to the minus 10 meters. And so just to give you a scale here, 1 millimeter, which is what you see here, is 10 million angstroms, right? If you compare that to the population of Michigan, Michigan has 10 million people. And so if we were to invite all of Michigan to come for a Badgers game and have them line up in a line, now imagine that line and now shrink it to 1 millimeter. That's the atomic scale. That's the kind of scale we're talking about. Okay, so you might ask then, if it's that small, how do we see it? Well, it turns out one thing that really comes in to help us here is one of my favorite types of objects, and these are crystals. Right? So in a crystal, what you have is a regular array of atoms that repeats through space. And what you can do with crystals is you can shine X-rays on them. X-rays are types of light, or a type of light that has a wavelength that has a spacing that's comparable to that of the spacing between atoms, right? They have the X-rays have wavelengths of about 1 angstrom. And so when you shine X-rays on a crystal, the X-ray as it passes through will bounce off of atoms at different times. And because this wave is hitting the atoms at different points in space, those X-rays will be scattered. There are certain directions at which all the atoms in the crystal are scattering at the same time, or in phase with each other, and this gives rise to a resonance, where you see a peak on a detector as the X-ray bounces off of the crystal. And so from the distributions of these peaks, you can actually tell what the repeat unit size is that forms your crystal, and then what gives the differences in intensity are how the X-rays interfere with each other as they bounce off of different atoms inside this repeat unit. And so the intensities of these reflections actually then tell you about the electron density inside your crystal. This is a wonderful technique, this technique of X-ray diffraction, because it's one of the few techniques where you can actually see the atoms and move them around on the computer screen and visualize them. And so, what's special about crystals? Well, we see big crystals at the mineral shop and think, that's a nice crystal. But it turns out that almost every metal you talk about at the microscopic level is actually made out of little crystals, right? And so you can take a little bit of metal and find that if you put it in the diffractometer, you'll see that it's actually based on a unit cell like this that then repeats through space to form a macroscopic object that's three-dimensional. And so really the way this works is that although we're talking about things at the atomic scale, when X-rays pass through it, that magnifies on the macroscopic scale, so you actually see peaks in your diffraction pattern. And so the question then is, what is the variety of ways the atoms can fit inside these unit cells, and what are the different kinds of cells that these structures can form? And so it turns out people have been trying to do this for a long time. I showed you 3,000 years of mixing metals together. And so we've started to collect some data on this. But you can see that, when we talk about intermetallic compounds, these are compounds that form when we mix metals together. This is the periodic table. You've seen this before. This part of the table is not metal. The rest of it is. And so when we talk about chemistry, really where most of the chemistry is what's going to happen when you mix different metals together to form compounds, right? And so we've been doing this for a while. So here are 4 volumes of reference data on these types of compounds. This is the state of the art of the knowledge in the 1990s. Since then, people have stopped printing these books because it gets expensive, right? And so right now you just have databases that contain thousands of data of these kinds of crystal structures that we see here. And so really this is a diversity which rivals that of other areas of chemistry, but we don't have simple rules to explain it all. And so what we're doing in my group is we're trying to understand why it is that at the atomic scale, the elemental metals, things like sodium metal, cadmium metal, gold metal, oh my goodness. Here we go, okay, go back. Yes. Why they form these simple arrangements like you might see if you put apples together in a supermarket, right? You have this square base and you put an atom on top of it, then you make another square base, right? These are very simple patterns that you can get. But if you take different metals and you start to mix them together, very different things can come out. So here is sodium metal, here's cadmium metal. If you mix them together in a 1 to 2 stoichiometry, you can make new crystals. This is this material that I showed you here earlier. Now, it turns out this is also a crystal that's based on a unit cell that's repeating. But in this case, this unit cell looks like this. It's a 30 angstrom cube this time that actually contains 1,000 atoms in its repeat unit. So before, sodium seemed like it wanted to pack like an apple, right? These guys want to pack like chaos, right? I'm not quite sure what's going on here, right? And so the thing, though, is that because we've gotten so big, we actually have much less going on. You can see this is only 300,000 cells per unit cell. So you take that line of the population of Michigan, fit it into a millimeter. Now we can just put Madison within a millimeter. You can see it's better, right? It's not quite as crowded. And so the thing, though, you can see here is that Linus Pauling was looking at this in the 1920s, right? People have been studying these types of crystal structures for more than 100 years, right? And we've gotten pretty good at solving these structures. Like people are doing things like solving structures that have 6,000 atoms in a unit cell or 23,000 atoms in this repeating unit, but we still don't really understand what's driving this. And so what we do in my research group is we try to combine theory and experiment to try to work out what's driving these very complicated arrangements from forming versus very simple ones where you just have atoms that seem to pack like spheres. And so we start out with these types of crystal structures that we're interested in. We'll try to develop new ways of thinking about them that explain why this complicated structure forms rather than a simpler one. And once we have those ideas, we'll go back and try to make new things, and it ends up being a little uncomfortable as we find out our ideas did not quite line up with what we were expecting, and so we end up with a lot of cannibalism? We end up having to rethink our ideas, and this is actually a symbol of renewal, so I think it works. But I told you that we're interested in using chemical ideas to explain this, but I'm really willing to try anything. In fact, I encourage my students to anthropomorphize, right? And so, if imagining that atoms have feelings helps, then let's do it and just try to understand what these atoms are trying to do. So here's a comic that one of my students made about transition metals coming together with the help of main group atoms to form these things that we call isotope bonds. And look, this one's feeling underappreciated. Yes, atoms have feelings, at least in my imagination. And so we'll see some more examples of this. And so really, a question is, what's going on in terms of getting unit cells that have thousands of atoms in cases where atoms really just seem to want to be, we would normally think about them as packing like spheres. And so if we start looking at the structures themselves, we can see some clues. So for instance, this sodium cadmium strip structure, this 1,000-atom unit cell, it actually, if you look in more detail, you see that there's this one unit that occurs a lot. It's called a Freehoff polyhedron. You can see it's an atom with these red atoms that form a tetrahedron around it, and then there's this blue cage around it. But the structure doesn't stop there. It takes these Freehoff polyhedra, and then it assembles them into these pentagons. And so we have pentagons of Freehoff polyhedra, but it doesn't stop there. It then takes these pentagons and then assembles them into these 6-sided figures. This would be an octahedron. And you can see that's huge, right? You can definitely see that if this starts to fill space, that might be the box we would need, right? And so how do you get complexity? Well, you take a simple object, you make more complicated objects of them, and then you make those objects packed together to more complicated ones, and then you keep going. And so as I was seeing different kinds of structures that do this kind of thing, I decided, why not look at the most complicated things we can imagine? And these are what are called quasicrystals. So these are systems where they show the diffraction peaks you would expect for a nice long-range periodic order structure, but they're arranged in patterns that don't make any sense. So you know that you can tile your floor with squares. You can also do it with triangles or hexagons. But if you try to do it with pentagons, it doesn't work, right? You end up with gaps. If you try to do it with 12-sided figures, that also doesn't work. You're going to end up with gaps. But here we have a diffraction pattern that, look, you can rotate this by a 12th of a circle. It looks exactly the same. There's 12-fold symmetry here. So somehow this object is trying to develop a 12-fold symmetry, even though you can't do that with a normal crystal. And so there are ideas about how this might work. This is called Shapley tiling. And the basic idea here is that you can take a dodecagon. This is a 12-sided regular polygon. And you can actually divide it into squares and triangles, where that seems like a nice way to go. But you see that now that we have these squares and triangles, you can actually put a ball on each of those corners. And you can actually go back to having dodecagons, right? And once you have those triangles and squares, you can start putting dodecagons on those. You see that you can make another way of making long-range order by just exchanging squares, triangles, and dodecagons, and just keep making it more and more complicated. I thought, that's really cool. Why would atoms want to do that? And so we started thinking about, well, why do atoms want to do anything? It's because they have feelings and desires just like we do. And so, so we can think about this. Here's the way I start out with this. Do you see that in metals, atoms like to pack very densely? And so you can see that you might have an atom here with 6 neighbors around it. And I drew this in kind of a very sciencey way first, which is that, okay, this atom wants to have contacts to all these. Do you see if these atoms wanted to get closer together, it probably couldn't do it without making these ones closer. You see there's going to be some cooperation that's going to happen here. And so I think, though, to make this more meaningful, let's think about this more like an atom feels. Imagine that we have a Kurter burger here, and these atoms are hungry. And so you can imagine that if you had Scoopy wanting to eat this, there would be no problem if it was just one Scoopy, right? Because it can get as close as it wants and it will eat it. But if you have 6 of them arranged around a Kurter burger, do you see that what's going to happen here is that if these guys want to get closer, they're going to start to bump into each other, right? And so the way I would describe this is that we have a potential bond that's forming here between one Scoopy and the burger here. But Scoopy doesn't want to eat itself, and so you can see that there's going to be a repulsion here. Now, if you were to walk around in this structure and say, what do I feel if I go here? You might feel like there's some suction, right? Everything's sucking inwards, trying to get closer to each other. But if you were to go over here, you might see that, I'm being squeezed because these guys are trying to squeeze into the same space. You might feel a positive pressure here and a negative suction here. And so one thing we've been doing has been to take quantum mechanical calculations, the kind of ways you would model these types of intermetallic structures, and say, where are the local positive pressures, where are the local negative pressures? And so our pictures don't really look like this. They look more like this, which is where you have atoms on the corners here, and you see we have these lobes pointing different directions. These are the directions where the atom feels negative pressure, where it wants to get closer to the things around it. These are the black lobes. They're like black holes in the structure, asking the structure to contract. But the structure can't contract around this poor atom, where it has these atoms that want to get closer, because you see the atoms in the surroundings, you see they have these white lobes. These are the positive pressures. These are the contacts that are already too close to each other, and the structure is trying to pull apart at these places. And so you end up with this frustration where this atom wants to get closer to everything around it. It's too small for its environment. But these guys are bumping into each other and can't get any closer. And so once you have a setup like this, you can start to think about why would crazy things happen in metals. So let's go back to our story here about how you would get 12-sided figures. Well, you can see these 12-sided figures they've made out of triangles and squares. And they're actually crystal structures that consist just of these triangles or just these squares or some other mixture. If you look at how the pressures are acting inside of these, we can say, well, what happened if I just took squares and triangles alone and then mixed them? Well, you can see that there are pressures here. There are pressures here. They're pretty big. But do you see that as I go from here to here, those pressures have gotten a little bit smaller? Something good has happened by mixing the squares and the triangles. And so you can actually go with this and say, well, what happened? Well, we see if we put a square and a triangle together, we have positive pressures. Those are the white lobes. Something about the big positive pressures here going away when we go to here, there seems to be something good there. And if we just go through it layer by layer, this atom is going to join to that one. Do you see positive pressure? Nothing. When they combine together, it's close to nothing, right? Something happened where the positive pressure went away when it was merged with something that wasn't under a lot of stress. Similarly, you see there's this big positive pressure here. When it wants to mix with something that not much is going on, it actually ends up being relaxed, right? And so what seems to happen is that when you have the squares propagating by themselves, they build up this pressure. When you have the triangles propagating by themselves, they build up this pressure. When you mix them, they kind of soothes itself. And so you can see this in more detail here, where if I just draw a plane through that and say, how much pressure is there on this plane? You see big positive pressure here, nothing here, big nothing here, big positive pressure here. Basically, when you mix the triangle units and the square units together, there's a possibility for something new to happen. Whereas before, you can imagine the squares and the squares, they're bumping together like this, where the positive pressures are bumping into the positive pressures. When you mix the squares and the triangles, they now interdigitate, and now they can just slide together easily together. And so you can then see that actually in some of these other structures we see that the squares are completely surrounded by triangles. The triangles are mostly surrounded by squares. It seems like they really like being next to each other. What happens when you go to these decagonal units, though, is we start getting more triangles touching triangles, and you can actually see this. If you take this structure and now you start mixing a third element in, this would be like silicon. You can see this is without the silicon. You start putting silicon in. Do you see this starts to change the way these pressures look? You see the triangles no longer mind being next to each other as much when you put a silicon atom in. And so by just tuning the elements a little bit, you can start to change the way these things talk to each other. And you can very easily go from saying, we want squares only next to triangles, and triangles as much as next to squares as possible, put a little silicon in. Suddenly, the triangles don't mind it as much, and now you can get these 12-fold figures. So we've gotten from triangles and squares to one unit of dodecagons. Now we have to go next to dodecagons, getting to triangles and squares, and then backwards back to dodecagons, right? But this is as far as I can take it today. So yeah, here we are. Great. And so this gives you an idea, though, of how doing a little bit of anthropomorphizing, we actually don't, but I mean, thinking about these in terms of what are the atoms trying to accomplish can really help you explain why atoms at this little scale can make things happen at this much bigger scale. And so with that, I'd like to thank my research group who has done almost all of this work, and I'd like to thank you for being willing to listen to me rant about the atomic scale. So great, thank you.
Good evening. I'm Swamit Tanu from Department of Computer Sciences. Kathy is helping me with my slide number 1. So, because I think, yeah, we can maybe do my best. Yeah. When we, let's say, play a note on a piano, can you play it, please? Thank you. There is a tiny hammer that hits a metal string, the string vibrates, and it generates a sound, right? And we could do the same thing. I'll try my best to play A minor in the right scale. The app detects the note, calculates its waveform. It does a bunch of calculations very quickly, and it plays the sound, right? And you can think about this as a simulation where we are simulating instruments, and with this iPhone we can simulate a guitar, drum, almost have a jazz band on our phone, right? So how far we can stretch this idea of simulation? Can we simulate an orchestra? Perhaps we can. but it's not going to sound as good as hearing them play in person, right? And the reason it's very hard to simulate orchestra is you're modeling each and every instrument in a lot of detail. You're also trying to simulate the interaction between these instruments, room acoustics, because every surface in this room is echoing sound, and that creates a very unique signature, right? So simulating systems is a really important, has a lot of applications. It's a really hard problem, may it be simulating an orchestra or simulating a molecule, right? So simulation of molecules, as Danny explained, has really interesting applications. We can learn about how metals form, how these molecules interact with each other, and if we can accurately simulate some of these systems, we can accelerate drug discovery, manufacturing of fertilizers, modeling new materials, and it has plenty of applications in finding new energy sources. So, for example, this molecule is something that you can find in a little bacteria which takes the environmental nitrogen and hydrogen and creates ammonia at room temperature. If you want to do this at industrial scale, you need a really hot environment with a lot of pressure. So manufacturing fertilizers is a very energy intensive process, and if we can learn about this molecule, how this molecule does this, we can lower the carbon footprint of manufacturing fertilizers, right? So simulation again can help us, especially at atomic scales, solve some of the very important problems that we face today. But these atomic scale simulations are extremely hard on conventional computers, and today I'll try to explain why that is and how quantum computers can help us solve some of these really hard problems. So if you picture an atom, probably this picture pops in your mind. This is a classical model of atom, something that we all study in high school. But unfortunately, atoms are not as simple, even the hydrogen atom with just one electron, right? So it's not really a correct model, and you have to use quantum mechanics to describe what an electron is doing. An electron is not a particle, it's actually a probability wave where you cannot confine it to one part of the space. It just occupies a really large space, and then you have to talk about in terms of what is the likelihood of finding an electron, right? So think of this as a cloud of electrons rather than just tiny particle. And when we are building simulations, when we are thinking about predicting properties of molecules, this creates a lot of problems, right? For example, when you have a very large molecule with many electrons, any electron can interact with any other electron, and you have to consider an enormous number of possible electron arrangements. And as the number of electrons in your molecule increases, this explodes, and it might take hundreds of years to simulate just one molecule using the fastest supercomputer that we have today, right? So we cannot do accurate simulation at atomic scales, not for large molecules. So this problem is something that quantum computing tries to solve. And the idea was proposed by many people, like a couple of people independently, but Richard Feynman talked about this idea publicly in his 1981 talk. And the idea is, if you want to solve a computational problem that is trying to model quantum mechanics, perhaps we can use some of the quantum elements in the machine or the computer that we are building itself. Right, so the idea is to use quantum mechanics in our devices to represent information, and then we utilize those devices to build a universal quantum simulator. So you use atoms to build a computer to simulate a molecule. That's basically the idea, right? And if you compare this with conventional computers or classical computers, there is a striking difference between how we build classical computers. So classical computers, like my iPhone, uses bits where the state of a bit is either 1 or 0, right? The state is either 1 or 0, and it's basically a switch. So no matter how large is this classical computer, you are just flipping bunch of switches, right? If you think about a quantum computer, on the other hand, quantum bit represents a significantly more complex system, right? So state of a quantum bit is any point on the sphere, not just 2 points, 1 or 0. If you literally want to represent 1 qubit using bunch of bits on your computer, 1 qubit can be represented as like maybe 64 bits. But as we scale, when you want to represent 10 qubits, if you want to express a equation that has 10 qubits in it, then you need 64,000 bits, and this grows very, very quickly. And when you hit 60 qubit, it's probably there are more stars in the Milky Way galaxy or something like that. I don't remember the exact analogy here, but it's a really large number, right? And even if you go through all these states with a very fast pace, let's say you are exploring billion states per second, getting through all these 60 qubit states would take 36 years. So it's a very large number, and the amount of information that 60 qubits is encoding is enormous. So then the question is, how do we really build these qubits? Is it just a mathematical quantity, or is it something that we can build in reality? And the answer is we can build these qubits either by using atoms, which are quantum mechanical objects themselves, or we can use superconducting circuits at very low temperatures. So in fact, this year's Nobel Prize of Physics has gone to 3 researchers who have demonstrated that by using macroscopic circuits, you can harness quantum mechanical properties, right? So you build a circuit, cool it down to really low temperature, it starts behaving as if it's an atom. It's like a small object, although the object is quite big. So today I'll talk about atoms trapped in laser field, right? Because that's easy to explain. So here is a picture that shows how this quantum computer would look like. So there are a couple of neutral atom machines on campus. They can trap hundreds of atoms and utilize those hundreds of atoms as qubits. So what we do is use lasers to pin these atoms, because atoms are really, really small, right? But if you use the right set of lasers, you can trap them in space. And you use another laser to manipulate its state. So you have an array of atoms trapped in space. You use another laser to change their state. So it's like writing 1 or 0 to these atoms, or changing its quantum state. And when you want to understand what is the state of these atoms, you take a picture, right? You take a picture with very sensitive camera, and then you are able to read these states out. So it's not fiction. I mean, there is a lot of work going on in academia. There are companies, top tech companies are building these quantum computers at really large scale. So for example, this is a picture from IBM. They are expecting to build a large data center scale quantum computer by 2033. They have made enormous progress in terms of engineering these devices. And there are a couple of other companies. There are very promising startups. Some of them are based in Madison, Wisconsin, which spun out of university. Right? So the reason companies want to build these quantum computers is because it's not just simulation. There are problems in optimization. There are problems in energy, problems in even maybe machine learning, where quantum computers can excel significantly compared to classical computers, right? So this is a really new area of computation. People have just started to think about what are the right programming models, how to design algorithms, how to design applications. And as we build more and more of these machines, I think new algorithms and applications will emerge. But how do we realize this, transformation where we have a problem that we want to solve, and at the bottom of the stack or at the end, there are either electrons, atoms, or photons doing all the work, right? So you go from problem to telling electrons what to do, and that's basically what a software stack or a system stack would do, right? So the first step is figuring out the algorithm. Algorithm is the recipe. Given a mathematical model of these quantum computers, we write a recipe, and then you take this recipe and write a program. But now there are tons of challenges when you go from an algorithm to a program, because there are a bunch of constraints that you need to satisfy. Right? On a quantum computer, for example, you cannot copy information. You are not allowed to make copies of your variables in the program, right? That's a big constraint. All of our programming models do not put such a constraint on copying, right? So now you need a programming language that tells you, hey, this is a legal operation, this is not a legal operation. You need a system that guides you to translate this algorithm into a concrete, correct, and clear recipe. And then there are compilers that translate this recipe or this program into steps that hardware can run, right? Many times algorithms are designed in a very sort of dreamy ways, right? And not all operations that algorithm designer want to support are supported on the hardware. So it's compiler's job to figure out how to translate these operations so that we can really run them on the hardware. And then the operating system is something that orchestrates these operations, and then lasers and cryogenics are again interacting with electrons, atoms, and photons. So my research focuses on compilers, operating system, and we also touch a little bit of qubit control. So programming quantum computers is kind of a challenging task, because you're really thinking about a very different mathematical objects rather than thinking about high-level programming ideas that are supported on existing computers, right? So mathematics is different. The way we realize this mathematics is also quite different. Modern computers don't really use lasers. We don't have to think about hardware errors that we will face on quantum computers. But interestingly, if you think about programming a quantum computer, we write these circuits which look very similar to sheet music, right? Where we are telling each and every qubit what to do at every point of time, right? So these funny looking symbols are basically manipulating the state of a qubit. We are utilizing sequence of operations to realize a particular function or particular algorithm, right? And then the compiler is something. It's a software piece that takes these instructions and turns them into sequence of pulses that our laser is going to shine on these set of atoms so that we realize this computation. So we have been working on building compilers, operating system, and our goal is to realize quantum advantage much before the hardware becomes very reliable. So the one of the biggest challenges, hardware is not quite reliable. So we have to reduce the operations which we want to perform on a quantum computer, right? So that also affects how quickly you can get the computation done. And we have been working on reducing number of operations, how parallelly we can do these operations, and the time to perform these operations. With the compiler that we have built, it's an open source compiler. We called it, we are not very creative, we are just calling it Wisconsin compiler or Wisc compiler. We can reduce the execution time by an order of magnitude. So, in summary, the scale that we are operating when we are working with quantum computers is really a subatomic scale, but at the same time, We can realize these systems because we have a enormous support from software, enormous support from operating systems, and so on, right? So our goal is to solve some of the hardest problems that we cannot solve using conventional computers. And I hope we make more progress, and maybe in next couple of years I can talk about what all problems we have solved in maybe a similar program. Thank you.
So I mentioned, hello. I mentioned at the beginning that this event is, of course, part of the Science Festival, but it's also part of Klez Fest Midwest, which is a Klezmer music festival in its second year now, and this is going to be a continuing annual thing. And I put this together with two of my partners who are sitting here in the front, and we're going to be talking about klezmer music today. And it was really interesting hearing the talks are always so interesting, but seeing how what both of these presentations ended up what was resonating for me was the way in which stuff was organized in these different parts of our world. And our world is very complicated, but it also has this deep organization. And music is very similar. Music has a deep organization, but rather than being an organization of objects, it's an organization of sounds. And that may seem like a crazy idea to you, but if I ask Kathy to play, Kathy, can you play just a 5/1 cadence? You can hear that last chord feels like home. It sounds like home. And in fact, so we have this organization system of chords, but we also have an organization system of keys of within our home territory. We have scales. And so we're talking about atomic scales here, pardon the pun, but here in this presentation, we're going to talk about musical scales, and I hope you'll permit the word association. So something's going on inside this piano here, but I'm going to need you.
Yes, I got you.
Okay. So I'm going to ask Kathy to play a C major scale for you.
Yep.
And you can hear that first note and that last note, which are the same note, they feel like home. And we have this pattern of leaps. So we have our first leap from C to D. It's called a whole step. And there's actually a note that's a half step in between those two. So from C to D, that's a whole step, and now we go up another whole step, and then a half step, and then a whole step, and a whole step, and a whole step, and a half step. And that's called a major scale. So we have right here a C major scale. And a piece that's written in the key of C major uses the architecture, and if I were good about this stuff, I'd have some kind of crazy diagram I could show you, but I'm not good at that stuff. But this is kind of the architecture of a key that a piece is in. And we can do crazy things to switch keys, and we can also have different colors of keys. So I'm going to ask Kathy to play a C natural minor scale. And then a C major scale again. So those two scales have a different tone, a different color, a different feeling to them. When we teach this to little kids, we say major is happy and minor is sad. And the scales, the organization of the scales just has to do with where the half steps are and where the whole steps are. And we could build our own scale, and we could have different patterns of whole steps and half steps. For instance, let's start on C, and I'll tell you how far to go up each time. So go up a half step, now a whole step, now a whole step, now a whole step, half step, whole step, whole step. So that's not major or minor. And when we have a scale that's not major or minor, we usually call that a mode. And in fact, all the way back in the medieval period where the music was usually just a single voice, there was a deep understanding of the construction of different modes and the feeling that those modes give. Klezmer music unfolds in its own set of scales, its own set of modes, and that's part of what makes klezmer sound like klezmer. So if you play a C harmonic minor scale for us. Something pretty cool happens at the top part of that scale, right? Show us from G. We go up a half step, and now a big jump, and then a little one, and a big jump down. And that scale, which we call harmonic minor, is that jump in it is a part of what makes klezmer sound like klezmer. And there are lots of different klezmer modes. So David, can you just talk a little bit? Let me get you the other mic. Could you please talk about some of the different kinds of modal structures that klezmer uses?
So you talked about the harmonic minor, but that started on the 5th degree in conventional classical music. But I would start, let's say if you're in C and G is the 5th degree, but I would call that scale, some people say, oh, that's C harmonic minor, but I would call that G Phrygish, because like a G Phrygian, basically. So, if I'm going, wait a minute, I'm all mixed up because I calculate it from the root.
So the jump happens at the beginning of that mode.
So there's a half step at the beginning. And you all know the scale because
so you can hear those jumps are what give klezmer music its very plaintive quality. And I would say, like many things Jewish, klezmer music is both happy and sad at the same time. And that it's like, things are great, oy, 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 and those are combined.
you could say that about Beethoven too, actually. Listen to the late Beethoven string quartets, you know, I'm fluctuating between incredible ecstasy and wanting to kill myself, so...
Okay, so these kind of melodic scale sides are only part of what makes klezmer klezmer. So when we listen to what you just did now or the piece that you started with, there's a lot of, and this kind of gets to the small scale. So we have our notes, and in Hava Nagila, if you could just play it without any ornaments, with no ornaments at all. But when David plays that, you'll see that there's little events that happen within that big structure. Again, I need one of you guys to make a scientific picture of this, but you'll all hear it. So in music, we refer to that as ornamentation for good reason. It's basically covered in bling. In this case, there's no subtlety at all. So what are you doing? Like, can you slow that down? Slow it down a little so people can hear the ornaments. So we have these boip, boip, boip kind of things. Talk about those.
Well, that's called, in Yiddish, the word is krechts, which means to sob or to squeeze. And so it's basically like a swallowed note. It's a note, I finger the note, but I stop it with my tongue. So basically it's kind of, and I use, when I teach that to people, I say use the syllable bite, bite. So you stop it like a bite, ba, bite, ba. You know, so that was sort of a clinical demonstration, but next question. But it's actually used for expression because the krechts, or this little stopped note, to me is like a catch in the voice when the emotion is so intense that it's like you're sobbing, like your voice stops. So it.
I remember recently reading a story about a violinist whose father played klezmer violin, and this little kid was learning to play the violin from a traditional violin teacher and learning the scales and where to put your fingers. And her comment was, yeah, but you're not making it weep. My dad makes it weep, and this kind of makes it weep.
And as the great bluegrass fiddler Vassar Clemens said, I like to make my fiddle cry. So, so it's very, yes, and it's very universal. But the klezmer, that's the klezmer way. In jazz, when you hear ghosted notes, if you hear someone go da 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 dum, you know, that doesn't sound like jazz. But if they go ba 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 ba, they ghost and swallow notes, and that gives swing and that gives expression.
And that's one reason why classical players often have trouble switching over to jazz, because we're taught to enunciate every note perfectly, because that's the style in classical music. So different styles cause for different kinds of ornamentation. And in fact, I would argue that hearing the ornamentation, you know what the style is right away.
Yeah, I think if, I said, bonjour Dan, je parle français, you would be, so you have to, one has to roll one's R's, and even though they say you can't really lose the accent of your native language after about age 4, but still, I learned to speak French. I could say, bonjour Dan, comment ça va, vous parlez français? I'm going to roll my R's, I'm going to make an effort to speak correctly.
So when you play klezmer, you're styling the music, and in fact, probably the music that you're reading just looks like if you were reading something by Beethoven, but you apply these various stylistic things, some usually on the small scale, through the ornaments, and that brings it off the page. So that takes you from bum 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 ba da bum ba to bye bye ba ba, and it seems like you have bends and you have trills. Can you show some of that stuff?
Same damn tune. One thing I
Abbott and Costello here.
One thing I learned about, in classical music, you see TR above a note, so you trill. Be a good player and do what's on the page. But when I started to play klezmer music, I realized that when you trill, it's like and I guess this relates to all the lectures, to atomic particles, and when you get to that saturation of emotion, well, you have an atom bomb, I guess. But it's that the trill is when you just can't hold it in anymore, when the note will not support just being played, it'll just smash. So you have to trill.
So what's great about this music is that much of it, 90% of it, is kind of improvisatory, and very much your own interpretation. You're not just playing the notes that somebody else wrote at all.
Not at all, no. I mean, yes, there are melodies that I adhere to, but then one is supposed to, it's part of the style, is supposed to add the ornaments, is supposed to add the trills. So, you know, a piece that I've championed for many, many years, Osvaldo Golichov's Dreams and Prayers of Isaac the Blind, he writes, it's for klezmer clarinet and string quartet. And I even got people saying, is that a special kind of clarinet? I said, no, it's a Selmer, you know, it's my clarinet. It's just a regular clarinet, the same clarinet I've been playing since I was 10 years old, the same kind of clarinet. But it's a style. So and I joke with Osvaldo, I say, I play every note you wrote, plus I give you 30% more. So, that is...
Did he raise his fee for the piece?
Not yet.
Are there other klezmer modes that we might listen for besides the Freygish that you played?
So starting on the same note, on the D, there's a mode called Mishberach. So Freygish, you know, these were modes that came actually from, Torah cantillation originally, I suppose. I mean, it's very hard to trace these things, but eventually people started to harmonize them to put, major and minor harmonies. So Freygish is harmonized in major, but then there's another mode which is called Mishaberach, and Mishaberach is harmonized in minor. So it starts off like a regular minor scale, but then goes to a sharp 4. Instead of, and the harmonization is. Then Mishberach. Sad. Happy.
So under the structure of what we just hear as really cool music with a lot of ornamentation and a lot of emotion, like entirely emotion, there is this deep structure. And without the deep structure, you probably wouldn't be able to create the mood at all. But for listeners, they don't have to know anything about the deep structure because the emotion is so present. Would you agree with my thesis?
I would agree. We'll just go around clockwise or counterclockwise. Yes, of course. I mean, I think that, I don't think people should need a manual to be able to appreciate music. Music should be, in my view, very, very direct and very visceral and very immediate. And that doesn't matter what music. One of the great modern classical composers, Lutoslawski, I saw him as a young person, saw him conduct his Third Symphony. And he had these little boxes that he gave the orchestra, and he gave them little improvisations, and he motioned to the orchestra, and I could have sworn it sounded like the roar of a crowd. And this was 1984 or something, and it was, solidarity in Poland, and these big demonstrations, and it was chilling. And, this is music that's supposed to be impenetrable, ununderstandable, and it was so immediate and so visceral.
That's a great description. Thank you. So I want to let the performers perform because I'm dying to hear them, and you are too, I'm sure. I just want to, with your permission, just go through the schedule for the rest of our Klezmer Festival so that you can come to our other events, and then I'll let you guys play.
Sure.
I'll take your mic off your hands. So tomorrow at 11 a.m. we have a children's concert just across the lobby in the Lee Kaufman Rehearsal Hall. My colleague Michael Bell and his daughter Eleanor Meyerfeld are playing a children's concert, and please come and bring your kids. It's going to be great for kids. There's going to be, I think, drawing and body movement and lots of fun things with Klezmer music. And then David and Kathy are playing the showcase concert at 2 p.m. tomorrow with their band, the Lower East Side Legacy Band, and that's going to be in here. Everything Klez Fest is completely free. So that's thanks to our sponsors who made this all possible. And so I think it is time for you guys to play for us. Thank you so much.
Thank you. Thank you. So now this mode that we talked about, we're going to put it into action, and not with Hava Nagila. This is a piece by John Zorn, the avant-garde saxophonist and composer from New York City. And so he formed a movement called Radical Jewish Culture. I made the first record of radical Jewish culture on his label Tzaddik back in the mid-90s. And he did a series of pieces called The Book of Angels. So this is the angel, the guardian of the seventh heavenly hall, Parzial. And I'll just play you again this mode, this Phragish mode that he uses. So you'll hear the Phragish mode put to work. Kathy's, you want to set up the piece? Okay.
So this next piece is a tune by a really great friend of ours, great clarinetist, and New York-based Syrian clarinetist Kenan Ozmer. And this tune of his, November 22, was written for one of those rare Thanksgivings that fell on November 22nd, a very early Thanksgiving, unlike this year. And Kenan found himself at the home of dear friends a few years after moving to the US, found himself at their Thanksgiving table and had that feeling, coming away feeling really at home at the table of friends. And then wondering afterwards, having this thought to himself and wondering if he had lost a part of himself by feeling at home in a new place. And I think you'll hear that so well, and I'm going to let David tell you about the scales. There's two main scales that he uses, and they're straightforward scales, C natural minor and F natural minor, but there's a little twist at the end which actually ties into the Klezmer scales that we were just talking about. And the thing about this is when David comes to this music, you're going to hear that he brings his sound and his sensibility to everything that he does. So it's still always going to be David with his Klezmer influenced sound approaching this music. But I'll let you talk more about that.
Thank you. So, so Kenan is using standard minor scales, but at the end of the melody, he puts in the sharp 4, which gives it that Judaic Arabic twist. Of course, I was so thrilled. Kenan is an old friend of Kathy's and became a great friend of mine in recent years. And just to share this cross-cultural sharing is such a thrill for me. So you'll hear the little twist in the melody at the end of it. Oh, you want me to play it? So. But then at the end. Kind of transforms. You'll see.
For this next tune, we thought we'd do something a little different and take a look at the natural overtone series, which is something adjacent to scales. But if you take a look at a string instrument, or a string is a good way to think about it. And if you were to touch it at the halfway point and push down on it, like on a violin or a cello or anything else, you would get 1 octave higher. And then at the 2/3 point, you'd get another 5th, and then you'd get a flat 7, you'd get all sorts of other notes. And in the introduction to this next piece, you'll see I'm just doing the same thing. The piano is full of strings, and I'm doing the same thing, and just lightly touching on the copper strings, wearing a glove so as not to leave my finger juice on this beautiful piano. Basically this piece is built around, then it goes into a little section where you'll hear 2 main bass notes, which are these, which is the bass note of the piece, the tonic, and then the flat second. And this is a very common thing in bow music. This tune is called Berumbau. It's a piece of mine in my native South Africa. There are very, very beautiful instruments made out of what look like hunting bows. They are women's instruments in the area where I'm from. And these are Xhosa people's instruments. So especially the ones that I have studied a lot and that I absolutely love are Uhadi and Umkhube. And they basically look like small hunting bows, and they are resonated with the mouth or with a gourd on the chest, played by women. And so this is basically a homage to that. They use a lot of natural overtones, and they have these 2 recurring bass notes. And then because David and I live in New York City, near Duke Ellington's home, we get a whole lot of New York City crept in to what was supposed to be a meditation on being South African and being far away from home, but it got caught up a little bit in New York City. So this is Berumbau, and yeah, and then basically you'll hear what I did in the very opening. You'll hear those 2 bass notes, do, 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 being used as a basis for the structure throughout the piece. You'll hear it when David is improvising. You'll hear that. And you'll hear that all over the piece. So that's basically, the basis of it.
I just, you'll hear that I do natural overtones as well, but you're going to hear Kathy's on the, what string are you playing that on? The C string. As Kathy is also cellist, so the C string is very appropriate. So this is Berumbau. Sometimes Kathy tries to get the glove off in mid-piece, but lately, I don't know. It's been a 0 batting average there, but you've done great with that glove on. Amazing. The next piece we're going to play comes from the repertoire of a clarinetist named German Goldenstein, who came to the United States in the early 90s. He came from Moldova and was, traditional Moldovan and Moldovan Jewish musician. And he had many hundreds of songs in his head, and one of them is the song we're about to play, but later found out that this song was not a folk song, but was a composition by a gentleman named Emil Kreutor, an incredible accordionist who I actually met in Kishinev back in 1989, and we had an amazing time jamming, eating delicious biscuits, and drinking Moldovan wine, which was really, it's not as good as French or Italian, but it's not bad, and it was really good that day, I'll tell you. So Emil Kreutor, I later met him in the United States, just a charming, charming gentleman, one of the great masters of Moldovan music and Jewish music. So this is our treatment of it, where we think of that whole world that he came from, and it's our version. It's called Moldavian Journey. Oh, the scales. Oh, yes, this is Misha Berach in action. So look out for it. Thank you so much. So we have one more for you now. Well, one and a half, because we're going to do a traditional klezmer song, which is called Der Heiser Bulgar, and it leaps around between the two modes I talked to you about. There's a third mode I use called Romanian major. We're not touching that one. It's kind of like a major scale with a few other piquant notes thrown in. But this will be the Fraigish and Mishaberach going back and forth, and there will be a quiz at the end, and you can identify. But that tune was first recorded in 1923, and Eastern European Jewish immigrants were, the recording boom was starting, people were starting to record, and they said, wow, well, there's hot jazz out there, but we need a hot klezmer dance. So they called it Der Heiser Bulgar, the hot Bulgar. And I'm going to precede it with a solo piece of mine that is it's a quasi-composition, quasi-improvisation. Well, that also leaps through the different modes. Thank you very much. Thank you, Dan and Meg and everybody, all the organizers of Klez Fest. This is just so much fun, and we hope to see you at our concert tomorrow at 2 p.m.